All right, in this screencast, we're going to learn about the basics of electrical force. And to start, I'm going to review a little bit about gravitational force because there's a lot of similarities between electrical force and gravitational force. Just as a little review, you'll remember that gravitational force is kind of defined by Newton's law of universal gravitation. And a few units ago, we learned that that can be quantified, I guess, with this equation right here. If you know the masses of two objects and you know the distances between their centers, which is the r, and then that universal gravitational constant, big G. And that's true for any two masses in the universe have an attraction between them. So I want to just point out that the gravitational force varies inversely with the square of the distance between the centers of those two masses. That's this r squared term down here in the denominator. Okay, so if I double the distance between the two masses, the force over on the left side here is going to go down by a factor of that doubling squared, which is 4, since the r is in the denominator. And that's something referred to as the inverse square law. And we're going to see that's also true for electrical forces. It's actually true for a lot of different phenomena in the natural world, in the universe. Anything that's a point source of something follows the inverse square law. For instance, light intensity from a source decreases with the inverse square of the distance between the source and the observer. Same with sound, the same with radiation. They all follow this inverse square law. Okay, so we've got an idea of, kind of remembered what gravitational force is. I want to also point out that gravity is strictly an attractive force, okay? It cannot repel, it always attracts the two masses. Electricity, the electrical force, I should say electrical force, not electricity there. So let me just change that. Nope, I can't. So I'm going to just cross out electric. See if I can do this. Cross that out and say electric force. There we go. Electric force. Like charges repel and opposites attract. I'm sure you've heard of that before, and there's only two types of charge. There's a positive charge and there's a negative charge in our universe. So there's only two types of charge, and if you have two of the same kinds of charges, they want to fight and get away from each other, kind of like two poles on a magnet. If you put a North Pole and a North Pole together, they fight each other. If you put a North Pole and a South Pole together, they attract. And you'll see there's a lot of similarities between the electric force and magnetic force. So if I had two charges, if I had a positive charge over here and I had a negative charge over here, and they're separated by a distance r, the electric force can be described with this equation here. It's actually called Coulomb's law. Coulomb was a scientist back in the 1800s. Coulomb's law, which looks really, really similar to Newton's law of universal gravitation. Same form, but instead of a capital G, you've got a K, okay? And that K is called Coulomb's constant, and it is 8.99 times 10 to the 9th newtons times meter squared over Coulomb squared. Don't worry about the units. They will always work out so that you get newtons on the left side over here. And then I would say Q is the magnitude of the charge in units that are called coulombs. So we're going to measure the size of a charge in a coulomb. And a coulomb is actually a pretty big amount of charge. Something that's got a charge built up on it of 1 coulomb has a lot of charge. So you'll see that electrons and protons, for instance, have really, really tiny charges. Okay, so I just wanted to introduce the similarities between the gravitational force and the electric force. You see Coulomb's law, it follows the inverse squared law, so if I double the distance between those two charges, the positive and the negative, since they're attracting each other, it's going to turn out that if I double the distance, that the force is going to go down by a factor of 4. If I triple the distance, the force goes down by a factor of 9, okay? All right, a little bit more about, specifically about charge. The charge of an electron is, as I said, really tiny. It's negative 1.6 times 10 to the negative 19th coulombs. That is a universal number, a constant in our universe. Every electron, whether it's here on Earth or somewhere out in the universe, has that exact amount of charge, and every proton has exactly the opposite, positive 1.6 times 10 to the negative 19th coulombs. And all charge in the universe comes in increments of this charge. We call it E. Okay, so that little lowercase e there represents 1.6 times 10 to the negative 19th. Magnitude, not positive or negative. Just when you see E, it's just the magnitude of the charge. And to denote whether it's positive or negative, the problem usually puts a plus or minus in front of the E. You can't split the charge up into smaller pieces. So every charge in the circuits in your house, in your phones, and your TVs are in increments of, or multiples of 1.6 times 10 to the negative 19th. Usually multiples in the orders of, quadrillions, quintillions, A typical charge in a circuit might be microcoulombs, which is 10 to the negative 6. So you can imagine how many E's you have to add up to 10 to the negative 6. That's a really, really large amount. Charge is conserved. Now I'm down here. Charge is conserved. So like we've seen momentum, we've seen energy being conserved. We can't create or destroy charge. It can be transferred from one place to another or from one object to another. And there's different methods of doing that. I'll just list them here. It's not important that you understand them for the AP1 exam, but just so you know, friction is one way. Like when you rub a balloon on your hair, you are transferring charge from the balloon to your hair or from your hair to the balloon so that each becomes charged a little bit, and then you can push the balloon against a wall and it usually will stay there. So friction's one way of charging something. There's another way called conduction, which is contact between one charged item and another that may be charged or uncharged, and then induction, where contact doesn't necessarily have to take place, just putting something in the presence of a charged object, if there's a conductor involved, can actually charge both objects. Okay, so just know that there's three ways to transfer charge. Okay, let's talk about the forces of nature and where electromagnetic force and the gravitational force stack up. I should add some words here. Electromagnetic force, gravitational force, strong nuclear force, and weak nuclear force. So the four fundamental forces of nature are those. There are no other forces in nature than those. All the contact forces and things around us that we see, friction and you pushing on a table, things like that, those forces come about because of these other four forces. If it wasn't for these four, there wouldn't be any other forces that we experience on Earth that are created. So these are called the fundamental forces of nature. And if you had to rank them in order of strength, I wonder how you would rank them. So think about that for just a second. Which you think is the strongest, and then I will tell you. These two down here, you're probably not very familiar with because we don't see them on an everyday basis. They're on an atomic scale or a nuclear scale. Turns out this one is by far the strongest. This is the next strongest. Electromagnetic force is third, and gravitational force is by far, far, far the weakest. And you'll see that in the problem we're going to do right now. The reason we don't realize that is because we are surrounded by gravity every day, and we don't really have a good way to measure electromagnetic forces, so the gravitational force seems like the strongest force because we've got this giant mass, the Earth, underneath us, and it's creating a very strong pull on us. Let's do an example problem to kind of demonstrate the difference between the electromagnetic force and the gravitational force. The gravitational attraction, we're going to compare the gravitational attraction between an electron and a proton, when they are in a hydrogen atom, and we're going to compare that to the force of the electrical attraction. So the electrical force and the gravitational force. We've got all the information we need down here. I've listed the mass of an electron. It's 10 to the negative 31st kilograms, 9.11 times 10 to the negative 31st. Mass of a proton is almost 1,000 times or 10,000 times heavier. The value of big G is a constant, we've got that here. Coulomb's constant, we've already listed, but there it is again. And then the charge for each of those is the magnitude is 1.6 times 10 to the negative 19th. One's positive, one's negative, so the forces are, it's an attractive force. It pulls each towards the center of the other. And then the distance between the nucleus or the proton of a hydrogen atom and the electron in its lowest orbital state is this 5.29 times 10 to the negative 11th. So here is our two equations. So on the next page, I'll just go ahead and we'll put these in and figure out what the magnitude is. Okay, so the gravitational force is going to be that value of G times 9.11 times 10 to the negative 31st times 1.673 times 10 to the negative 27th, all divided by, I think it was 5.29 times 10 to the negative 11th meters. Okay, and then I'll go offline and get a number for that. Okay, first thing is I forgot to square this, so let me make sure I square that. And then what I just came up with was a number of 3.63 times 10 to the negative 47th newtons. Really, super small. Okay, how about for the electrical force of attraction between those two? Okay, that's going to be 8.99 times 10 to the 9th, that's Coulomb's constant, times just the magnitude of those two charges. So one's going to be positive and one's going to be negative. So if you multiply them together, you'd get a negative number. But all you need to know is the magnitude of those two, and know that if it's opposite charges, then they're going to the force will attract each to the center of the other. And then 5.29 times 10 to the negative 11th squared. Again, now you can tell this is going to be a bigger number for two reasons. One, these exponents here are a lot bigger than the negative 27th and a negative 31. But the other thing is, look how much bigger the exponent is in the constant. That's an indication that the force of electrical attraction and repulsion is a lot greater than the force of gravity for two given objects, okay? I'll go offline again and calculate this. Okay, so what I got on this one, what I got on this one was 8.22 times 10 to the negative 8th newtons. So compare this to that, it's almost 10 to the 40th times, approximately. That's 10 with 40 zeros, bigger. So the gravitational force of attraction is 10 to the 40th times bigger between an electron and a proton and a hydrogen atom than the gravitational force of attraction. So that really gives you a strong sense of how much stronger the electrical force is. And in fact, the electrical force is what holds everything together. All the molecules and atoms in a solid are held together by those electrical bonds. So it's a good thing that that's stronger than gravity. The last thing I'm going to point out is that, excuse me, is that the electrical force, you can have more than two individual charges that are interacting. I could have a system of 3 charges here, and you can tell from this drawing that because these two, this one here and this one here are opposites, they're going to have a force of attraction, excuse me, like that, and this one here is going to have a force of repulsion from this one. So this one, this one and this one are going to interact with a force like that. So to find out the sum of the net force on any one of these, you would figure out the the electrical force between each pair individually. And what I mean by that is to find out, for example, what the electrical force is, the net electrical force is on this guy right here, I would find the force of interaction with this one and the first one, and I would also find the force of attraction between the one here on the left and this one over here on the right separately, and I could just add them together because they're all, notice how I put them in a line, I could just add them in the x direction. If I wanted to find the interaction between this guy here in the middle with the other two, I would just find the individual forces between the one in the middle and the one on the left and subtract it, or actually I would add it because they're both pushing it to the left here, and then I would add it with the repulsive force between these two here and here. Okay, that's called superposition. So it's a matter of just calculating the forces individually between two objects and then adding them up or subtracting them as necessary. I've given you a very simple one because they're all in one dimension back and forth, like on an x-axis. You could have them positioned, like this, in space where they're, the forces are off at angles. Let's say that those two were like that, and then these two were an attractive pair right here. If I wanted to find the net force on this guy down here, I would have to find the vector sum of that vector and that vector. So it would look something like this. So the attractive force of this one on that guy would be pulling it a little bit to the right, and the repulsive force of this one on that guy would be pushing it down to the right, and when you add the x components and the y components together, you get this blue vector right here. Okay? I'm going to talk about circuits in the next screencast. This is just an introduction to the electrical force and conservation of charge and the charge on an electron and a proton. Okay?